Okay, third time's a charm. Sorry, Miss Sandy buzzed in here. All right, so what this is talking about on number 6 is just a fancy way to write the equation, okay? We wrote the exact same thing on number 4. I'm going to hit this check button, okay? If you notice, right here, this is what we just wrote, okay? So I'm just going to rewrite this. So 20 was our first term, okay? 3 was our common difference, and n minus 1 is our recursive definition, okay? So I'm going to put a first, common difference, recursive definition. This is a fancy way to say y equals. So, on number, or the second part of number 6, it says how many seats will be in the 21st row of the auditorium. So I'm going to use this equation again to find the 21st term, okay? So on the bottom part of number 6, I want you to write Tn equals 20 plus 3 times n minus 1. Now in this case, we're looking for the 21st term. So every time you see an n, you're plugging in a 21, okay? Now we're just simplifying. 20 plus 3. 21 minus 1 is 20. Simplifying. 20 plus 3 times 20 is 60. So we have 80. So in the 21st row, there should be 80 seats. I'm going to click off the markup, and we're going to check ourselves. And if you look, they did the exact same thing as what we just did, okay? All right, at the bottom, it says a function rule in the form of y equals mx plus b, which is what we just did on number 4 too, which is slope-intercept, models the situation, y equals 17 plus 3x. I believe we wrote it as 3x plus 17, but it works out the same way, okay? So, compare the function rule to the formula that we just did. How were they the same and how were they different? So I'm going to hit check. Okay? If you look, it shows both formulas. Okay? In the first one, 17 plus 3x. 17 is the y-intercept. Okay? It is the value of the function if x can take on a value of 0. So if we were to plug in 0 for x, we would just get 17. However, if we plug in 1, we have 17 plus 3, which is 20, which, remember, is our first term. Okay, so that's what that's talking about. The next equation shows that 20 is the first term. That's what we just said. Okay. The rate of change is 3. The common difference is 3. Same thing, okay? So it both works out. Either way is totally fine. I personally think that using the second one, using the nth term, I think that's a little bit easier and a little bit easier to recognize, okay? All right, so I want you to flip over to the next page, and on your number 7, let's see, right here, I want you to put a big X on number 7. Okay, we don't need that. It's not a part of our standards. It's really proven something, and we'll actually talk about it next week when y'all are here. But for right now, I just want you to put a big X on number 7. Okay. Now I want you to scroll down to number 8. Let me find it on here. Okay. And this is a reinforced. So this problem is not on your Agile Mind. It's kind of like a homework problem. Okay. So it says, consider the sequence -5, 1, 7, 13, 19, and 25. And it wants us to write a recursive definition, okay? And the general formula. So first, let's write the recursive definition. Actually, let's determine the common difference, okay? So my common, let's see. Pen's off. Okay. Common difference. How do I get from -5 to 1 and 1 to 7, 7, 13, 13, 19, 19, 25? I'm adding 6 every time. Okay, so my common difference is 6. Now, my first term is -5 right here. Okay, so I'm writing two equations. For one of them, I'm saying AN equals -5, okay, it's my first term, plus my common difference, n minus 1, okay? So that's one of them. If I did another, we would have a n minus 1 plus 6. So either one you use, you are going to get the same answers. So like on this first one, let's look for the second term. So I'm saying A2 equals -5 plus 6 times 2 minus 1. We're just simplifying. Is my second term 1? Yes. Okay, this works. All right, now on this second one, we're still looking for A2. So we have A2, and remember, every time you see an N, you're writing a 2. We're simplifying. A of 1, because 2 minus 1 is 1, plus 6. But what was A1? What did we just say? -5, first term. So we have a -5 plus 6, which also equals 1, okay? So either equation works, okay? All right, flip over to number 9. And we'll swap back to Agile Mind. All right, this part is what we skipped, so you can skip over that. All right, we're ready for number 9. So this says, but why use arithmetic sequences when linear functions will provide similar information? Return to the auditorium situation for a moment. Suppose the auditorium has 12 rows. What is the total seating capacity of the auditorium? Adding all the seats in row 1 through 12 is the same thing as finding the sum of the first 12 terms of an arithmetic sequence that represents the numbers of rows in each row. Okay? So I'm going to hit this play button first. It tells us that there are 20 seats in row 1. Okay? Each row has 3 more seats than the row in front of it. We've already filled some of this chart out. Okay, so all it's doing right now is adding 3 to each time. So while it's doing that, I want you to actually write this part out on your number 9. Okay? So I want you to pause for a second, and I want you to write this and this, okay, the top line and the bottom line on number 9, okay? So take a few seconds to do that. All right, now, nobody has time to add up all those numbers. If we have a calculator, yes, you can go for it. But a lot of times we don't have a calculator, so I'm going to show you a trick, okay? So I want you to hit this number 2 at the bottom, and I want you to hit play. And first, it says, look at the pair of terms. So I'm going to stop right there. So it's taking the first term and the last term, and it's adding them together, okay? Next, okay, it's going to take the second term and the next to last term. And you're getting 73. Okay? Do you think this pattern continues for the pair of terms in this sequence? Okay, we're going to hit this number 4. All right, there's the third. There's the fourth. There's the fifth. And last but not least, the 6th term. Okay? So, what I want you to do underneath where you wrote each term, I want you to write 20, 53 is 73. 23 plus 50 is 73. So I want you to write each set of terms. That's what I'm doing. 26 plus 47 is 73. 29 plus 44 is 73. 32 plus 41 is 73. And 35 plus 38 is 73. Okay? So, how many pairs do I have that equal 73? So you can count 1, 2, 3, 4, 5, 6. Or you can count the tally marks. 5 and 1. 5 plus 1 equals 6. So here's the trick. Okay? If you have 73 6 times, what is the easiest way for me to do it? Is it easy for me to add 73 6 times? No, not easy. But we can say 73 times 6. Okay? 3 plus 6 is 18. 7 plus 6 is 42. Plus 1 is 43. So the total number of seats is 43. I'm going to delete this, and it's going to show you on the next step what we just did again. Okay, so you're going to hit this number 5. And it's just counting the pairs for you. Six times 73. We're multiplying. And we get 438. So there are 12 terms. So that gave us 6 pairs. So let's say I have 20 terms. That's going to give me 10 pairs. So you're just breaking the number of terms in half to get your pairs because there's 2 in a pair. Okay? Each pair was added to 73. And I'm just multiplying to find the sum. 73 and 6 would give me 438 seats in the 12-row auditorium. Okay? All right, moving on.